Exoplanets, those distant worlds orbiting stars beyond our solar system, have captivated scientists and the public alike, especially with recent advancements in telescope technology, like the James Webb Space Telescope. The discussion among astrophysicists revolves around whether the James Webb Space Telescope has uncovered evidence of alien life on these exoplanets, focusing on the analysis of light from their atmospheres to detect potential biosignatures. This exploration highlights the transformative role of spectroscopy in understanding habitable environments, revealing how over 5,600 confirmed exoplanets offer a vast canvas for investigating life's possibilities in the cosmos. At the core of this inquiry is the method of spectroscopy, which deciphers the information encoded in starlight passing through an exoplanet's atmosphere. When light travels from a distant star, it interacts with atmospheric molecules, absorbing specific wavelengths that create unique patterns, much like a barcode unique to each chemical compound. For example, molecules such as water or oxygen have distinct structural arrangements that dictate how they vibrate or rotate, influencing the energy they absorb from light. By splitting this light into its spectral components, researchers can identify missing wavelengths, effectively reading the atmospheric composition without needing to physically visit the planet. This technique is pivotal because direct travel to these worlds remains impossible with current technology, making light the primary messenger of cosmic secrets. One of the most compelling scientific highlights is the search for biosignatures, particularly through disequilibrium chemistry. On Earth, the coexistence of oxygen and methane in the atmosphere serves as a key indicator of life. Oxygen, produced in vast quantities by photosynthetic organisms, and methane, often generated by biological processes or geological activity, are inherently unstable together. They react to form carbon dioxide and water. Their persistent presence requires continuous replenishment, suggesting an active source. In the context of exoplanets, detecting such an imbalance could point to biological activity, but only after ruling out non-living explanations like volcanic outgassing for methane. This approach demands conservatism. Claims of life must be backed by evidence that no abiotic process can replicate the observed conditions. For instance, oxygen alone might accumulate over billions of years from geological processes, but paired with a reducing gas like methane, it becomes a stronger fingerprint of life, as the methane actively steals oxygen, preventing buildup unless life sustains the cycle. The James Webb Space Telescope elevates this detective work by capturing infrared light from exoplanets during transits, when they pass in front of their host stars, causing a slight dimming. This allows for detailed atmospheric profiling, particularly on habitable zone planets, those at just the right distance from their stars to potentially harbor liquid water. Among the highlights is the observation of K2-18b, a super-Earth or mini-Neptune, where the James Webb Space Telescope tentatively detected dimethyl sulfide, DMS, a compound produced by marine life on Earth. DMS arises from biological metabolism, but on K2-18b, with its thick hydrogen envelope and limited surface light, alternative origins like photochemical reactions or geological processes must be considered. This finding underscores the James Webb Space Telescope's ability to probe atmospheres for exotic chemistries, pushing the boundaries of what we define as habitable. Super-Earths and mini-Neptunes, more common than Earth-like planets in our galaxy, challenge traditional models, as their higher gravity might retain gaseous envelopes, potentially hosting life in subsurface oceans or atmospheric layers. Another standout aspect is the historical variability of Earth's own biosignatures, informing how we interpret exoplanet data. For about 2 billion years, roughly half of Earth's 4.55 billion-year history, the atmosphere has shown detectable signs of life through oxygen-methane disequilibrium. This timeline suggests that exoplanets with similar evolutionary paths could broadcast their habitability over cosmic distances. Researchers have mapped nearby star systems using missions like Gaia, identifying around 2,000 within 300 light-years, where Earth could be observed as a transiting exoplanet, complete with biosignatures. This reciprocity flips the perspective. From those vantage points, our planet would appear as an alien world, emphasizing that life detection is about spotting anomalies in equilibrium, not just Earth-specific chemistry. Extremophiles further enrich this narrative, demonstrating life's tenacity in extreme environments. Organisms surviving desiccation, radiation, or volcanic conditions on Earth inspire models for exoplanet habitability, such as on icy moons with tidal heating generating subsurface oceans. Europa and Enceladus, for example, may harbor liquid water beneath ice shells where chemistry could concentrate to form life. This extends to speculative ideas like higher oxygen levels accelerating evolutionary complexity, as seen in Earth's Jurassic period, with 30 to 32% oxygen fostering larger life forms. Such worlds might be easier to detect due to stronger biosignatures, broadening the search beyond carbon-based, water-dependent life. In essence, these highlights illustrate how exoplanet studies blend observation with modeling to unravel habitability. By focusing on light's encoded Mander messages, disequilibrium indicators, and the James Webb Space Telescope's revelations, the field moves closer to answering whether we're alone, all while maintaining a rigorous, evidence-based stance. The hunt for life on exoplanets isn't just a serene gaze into the cosmos. It's a battlefield of ideas, where groundbreaking discoveries clash with skepticism, and the line between fact and fantasy blurs in the vacuum of space. Imagine the James Webb Space Telescope piercing the veil of distant worlds, only to ignite fierce debates. Is that faint signal a whisper of alien biology, or just cosmic noise? The recent detection of dimethyl sulfide, DMS, on K2-18b exemplifies this high-stakes drama, thrusting astrobiologists into a whirlwind of controversy. DMS, a pungent gas churned out by Earth's ocean-dwelling microbes, tantalizes with the promise of life. But on a bloated super-Earth, shrouded in hydrogen, could it be a geological imposter? This revelation has split the scientific community, with optimists hailing it as a potential biosignature breakthrough, while naysayers demand ironclad proof, warning against the perils of overinterpretation in our desperate quest to not be alone. At the heart of these fiery disputes lies the thorny issue of biosignatures themselves, those elusive chemical fingerprints that scream life or murmur maybe. Take the oxygen-methane duo. Their unstable dance in an atmosphere suggests something alive is fueling the fire, constantly replenishing what chemistry would otherwise extinguish. But here's the plot twist. What if volcanoes or photochemical reactions are the culprits, mimicking life's handiwork? Critics argue that our Earth-centric lens blinds us, assuming alien life must play by our rules. Why not silicon-based beings thriving in hellish heat, or exotic chemistries defying carbon's dominance? The controversy escalates when considering mini-Neptunes like K2-18b, where thick gaseous layers could brew DMS through non-biological means, turning a eureka moment into a cautionary tale. Skeptics point to past false alarms, like the 2020 phosphine detection on Venus that fizzled under scrutiny, reminding us how hype can outpace evidence. Yet proponents counter with urgency. If we wait for perfection, we might miss the galaxy's greatest show. Panspermia adds fuel to this inferno, proposing that life hitchhikes across the stars on meteorites, seeding worlds like cosmic pollen. Picture octopuses, those eight-limbed enigmas with camouflage skin and problem-solving smarts, as possible interstellar immigrants. Their DNA, so divergent from other Earth life, sparks wild speculation. Did they crash land from a distant exoplanet? Detractors dismiss this as fringe fantasy, insisting evolution alone explains such oddities, without invoking spacefaring microbes. But the debate rages on, especially with chirality in the mix. Earth's amino acids favor one-handedness, while meteorites show a 50-50 split. If we find mirrored chemistry on Mars or Europa, it could shatter paradigms, proving life reinvents itself independently or travels freely. Imagine the uproar. Are we all aliens, descendants of ancient cosmic wanderers? This hypothesis challenges evolutionary biology's core, pitting gradualists against those who envision a universe teeming with shared origins, where contamination between worlds blurs the lines of native life. Evolutionary timelines crank up the tension further, questioning why Earth lingered in single-celled simplicity for 3.5 billion years before exploding into complexity. Was it oxygen's slow buildup that unlocked multicellular marvels? Or could alien exoplanets fast-track this with Jurassic-level atmospheres? 30% oxygen fueling colossal creatures. Headlines scream alien dinosaurs, but purists cringe, arguing such extrapolations sensationalize science, risking public disillusionment if unproven. What if low-gravity moons like Titan allow winged beings to soar, or high-gravity super-Earths crush aspirations for intelligent life? These scenarios ignite ethical firestorms too. As we probe icy moons with plumes spewing potential biosignatures, NASA's planetary protection protocols become battlegrounds. One rogue microbe from Earth could contaminate Enceladus, forever tainting discoveries. Did we find alien life, or just our own reflection? The frustration boils over. Life is infuriatingly resilient, surviving depths that would melt our probes, mocking our attempts to sterilize spacecraft. Then there's the ultimate controversy. Are we too conservative, shackled by fear of error, or recklessly optimistic in a field ripe for missteps? The Habitable Worlds Observatory looms as a potential game-changer, promising to image exoplanet surfaces directly. But funding battles and technological hurdles threaten to delay this revelation. In this cosmic thriller, every James Webb Space Telescope data point is a clue, every debate a cliffhanger. Will disequilibrium chemistry unmask hidden biospheres or expose our biases? The stakes couldn't be higher. Unraveling these controversies might redefine humanity's place in the universe, turning exoplanets from distant dots into mirrors of our own existential drama. The universe, a vast, unforgiving arena where stars explode in cataclysmic fury and black holes devour light itself. Yet amid this chaos, exoplanets whisper secrets that could shatter humanity's solitude forever. As the James Webb Space Telescope beams back data from worlds light years away, the implications for astrobiology erupt like a supernova, forcing us to confront the ultimate thriller. Are we the lone sentinels in the cosmic night, or mere players in a galactic symphony of life? The detection of potential biosignatures on exoplanets like K2-18b isn't just science. It's a seismic shift, a plot twist that could rewrite our origin story, ignite interstellar dreams, and unleash ethical maelstroms that echo through eternity. Dive deeper into the heart-pounding ramifications. Astrobiology, once a fringe pursuit of dreamers, now stands on the precipice of revolution. The James Webb Space Telescope's infrared gaze has unveiled atmospheres ripe with disequilibrium, oxygen and methane locked in a forbidden tango, dimethyl sulfide lurking like a shadowy assassin on alien horizons. These findings propel us toward a future where habitable exoplanets aren't hypotheticals, but harbingers of destiny. Imagine the Habitable Worlds Observatory, the next colossal sentinel in space, launching into the void to image planetary surfaces directly, blocking stellar glare to reveal oceans, continents, or even artificial megastructures. But beware. The drama intensifies. Funding wars rage on Earth, with budgets slashed and priorities clashing, delaying this beacon of hope. Will we seize the stars, or let bureaucratic black holes swallow our chance to touch the infinite? The evolutionary clock ticks relentlessly, amplifying the stakes. Earth's own saga, 3.5 billion years of microbial monotony exploding into dinosaurs and civilizations, mirrors what might unfold on super-Earths or icy moons. Higher oxygen worlds could spawn alien dinosaurs in a fraction of the time, their biosignatures blazing across the cosmos like distress flares. Yet, this acceleration spells peril. If complex life arises swiftly, intelligent civilizations might self-destruct in nuclear infernos or climate apocalypses, leaving ghost planets as warnings. Yes, panspermia's wild ride adds to the frenzy. What if life's seeds rain from comets, contaminating worlds and blurring origins? Our probes to Europa's plumes or Enceladus's geysers could unwittingly seed earthly microbes, turning discovery into desecration, sparking interstellar contamination scandals that haunt generations. Ethically, the plot thickens to a boiling point. Detecting life on exoplanets thrusts us into moral quicksand. Do we broadcast our presence, risking invasion from advanced beings, or cower in silence? Fermi's paradox looms like a specter. Where are they all? The James Webb Space Telescope's silence, so far, could mean we're first, or that civilizations burn bright and vanish, victims of their own hubris. Future missions demand planetary protection on steroids, sterilizing craft to depths that defy imagination, lest we become the villains in another's origin myth. And the human toll. Astrobiologists grapple with existential vertigo. Finding life could unite humanity in awe, or fracture us in fear. As religions recalibrate and societies splinter over alien truths. But oh, the glory if we succeed. Envision a galaxy teeming with biospheres, titans, dense skies where winged creatures defy gravity, mini Neptunes with floating ecosystems harnessing temperature gradients. The James Webb Space Telescope's legacy fuels this vision, inspiring biolabs to cultivate extremophiles that mimic alien resilience, from radiation-proof tardigrades to deep-sea survivors. These models predict habitability zones expanding beyond Goldilocks confines to rogue planets wandering starless voids, heated by internal fury. The data cascade promises medical miracles, alien chemistries unlocking cures for diseases that plague us, or environmental salvation, learning from worlds that balance their atmospheres without tipping into catastrophe. As the curtain rises on this cosmic epic, one truth thunders. Exoplanets are no longer distant specks. They're portals to our fate. The James Webb Space Telescope has cracked the door, but the floodgates await. Will we decode the light's enigmas, unveiling siblings in the stars, or face the abyss of isolation? The universe doesn't wait. It's expanding, secrets slipping away at light speed. Humanity stands at the brink. Embrace the drama, fuel the telescopes, and chase the unknown, or risk fading into obscurity. The final act is unwritten, but the stage is set for the greatest revelation in history: life, everywhere, or the echo of our lonely cry.